Hello everyone, welcome to the problem solving session for analog communication nptel class. Today is the fifth week and today we will be continuing with amplitude modulation. So this is the first problem. For the first problem, which of the following signal is a characteristic benefit of using envelope detection for demodulating AM signals? So for demodulating amplitude modulation signals, what is the characteristic benefit of an envelope detector? So what does an envelope detector do? An envelope detector goes like this. So for an envelope detector, you have a AM signal that goes like this. So it is a sinusoid with varying amplitude, and the amplitude varies according to the message signal. So if we trace the peaks only, then we have something that is called an envelope. And since the amplitude of the waveform of the waveform here squarely depends on the message signal, so if we detect the message signal, it is equivalent to detecting if we detect the envelope, it is equivalent to detecting the message signal. So now it has, what is the characteristic benefit of using such a method? So one is it reduces the modulation index. Now this is not possible, as the modulation index mu is basically the ratio of the message signal amplitude and the carrier signal amplitude, and it is decided at the transmitter. So this is decided at the transmitter. So since this is decided at the transmitter and envelope detection happens at receiver, so it cannot be that we have reduction of modulation index at receiver. So this is not a characteristic benefit. Please mute yourself. So this is a characteristic benefit. So this is not a characteristic benefit because this is not possible at the transmitter side. Now, second option is that it minimizes the signal distortion. So this we will come to later. And next is it simplifies the demodulation process by avoiding the need for carrier recovery. So this is a strong candidate that you don't need any carrier recovery. You don't need to know what the carrier signal is. You will just do a peak detection. You will just do detection of the peaks, and by joining the peaks, interpolating the peaks, you will get the carrier signal envelope. You will get the envelope and hence the message signal. So this is it simplifies the demodulation process. This can be a good choice. Now it improves frequency stability. Now amplitude modulation has nothing to do with frequency, so this is squarely false. And now it minimizes the signal distortion. So here we are detecting envelopes, so it has nothing to do with signal distortion. Again, it can, because we are not dealing with the entire signal, we are only dealing with the peak values, and if the peak values get distorted, so will the message. We cannot do anything about that in this method. So the correct answer is option C. It simplifies the demodulation process by avoiding the need for carrier recovery. Next, why is coherent demodulation necessary for SSB-SC? So single sideband suppressed carrier. So in single sideband suppressed carrier, usually you have one carrier signal, you have one carrier in the frequency domain, you have one carrier, and you have two sidebands. You have one band at the carrier and you have two sidebands. Now in SSB-SC only this sideband is present. This is not present because it's a suppressed carrier, and this is not present because it is a single sideband. Now so here we will need to why is coherent demodulation necessary. Coherent demodulation means that you will have to exactly and accurately give the frequency at the local oscillator of the demodulator. So you have a local oscillator, you have a local oscillator of the demodulator. Now you have a local oscillator of the demodulator. Now you have to accurately give the frequency, exact frequency that was transmitted at the local oscillator, because you are only detecting based on the sideband. So to recover, so if you don't get to give this exact frequency, then you will not know what the exact carrier frequency is. So you will not be able to separate, because this is what, this is at Fc plus Fm, this is at Fc plus Fm. So you you will get this frequency FC plus FM. But if you don't know FC accurately, then you cannot separate FC from FM, right? So to recover the suppressed carrier, we need exactly coherent demodulation. Now, exactly coherent demodulation may not have been necessary in normal amplitude modulation signal. Why? Because in normal amplitude modulation signal, carrier is also present. So if your carrier is also present, then you can just get the carrier from the received signal itself, and then you can subtract the carrier from this sideband frequency to get the message frequency. But here there is no carrier frequency, so the carrier frequency needs to be supplied accurately externally, or else you won't be able to separate out the message frequency from the sideband frequency. So we need to recover the suppressed carrier, and that's why coherent demodulation is necessary. Next, which modulation technique provides the best performance in terms of bandwidth efficiency? So bandwidth efficiency means how much amount of frequency you are using to transmit a given information. So for the same information in a DSB-SC, what does a DSB-SC look like? DSB-SC means you will have double sidebands, but so each of them has a bandwidth of FM. So FM and FM, so the bandwidth is 2FM. In amplitude modulation, you will need FC plus 2FM. At frequency modulation, you have some FC plus delta F. And what is at FC plus delta F? And what will be the bandwidth in single sideband suppressed carrier? For single sideband suppressed carrier, you only have this. So here also you have 2 FM, here also you have 2 FM. The carrier is a single impulse, so it won't contribute to the bandwidth. So here carrier is a single impulse, but the sidebands occupy bandwidth. So each of them is FM and FM. And for frequency modulation is FC plus delta FM. So here the answer is 2FM, here the answer is 2FM, here the answer is FC plus delta F, and here the answer is just FM because you have a single sideband. So just FM. So clearly FM is smaller than 2FM and FM is much smaller than FC. So option D has the smallest frequency. So the smallest frequency is the single sideband suppressed carrier. Single sideband suppressed carrier provides both the best bandwidth efficiency among listed modulation technique because it transmits only one sideband and suppresses the carrier, utilizing the minimum necessary bandwidth. And then there is something called a vestigial sideband modulation. There is something called a vestigial sideband modulation or VSB. So in VSB modulation, by the way, another thing is that another way of writing AM is DSB-FC, double sideband full carrier. This is another name for amplitude modulation, DSB-FC. Okay. So if you suppress the carrier of DSB-FC, you get DSB-SC, and you suppress another sideband, you get SSB-SC. So, and another is vestigial sideband. Now VSB, in VSB, say VSB-SC, in VSB-SC you have only one, like in SSB you have one band, you have one sideband. In DSB you have two sidebands, but in VSB you will have some 1 point something sidebands. So it is a 1 plus eta, the sidebands. So you will have 1 plus eta sidebands. You will have 1 plus eta sidebands. So VSB-SC has 1 plus eta sidebands. Where were we? Yeah. So 1 plus eta sidebands. Now this will look like in practice, look like this, and here you will have something like this. So instead of allowing the full subbands, we create a band pass filter which only allows up to this frequency, or a high pass filter here which only allows up to this frequency. So you take some 0.2 of the total band, so you have 1.2 subbands like that. So this is called VSB-SC. So next question is, in context of VSB-SC modulation, what does the vestigial part of the signal refer to? So what is vestigial? Vestigial means something that is like remaining in fractions. It's not the whole that was. It's a part of the whole. It's a fraction of the whole. So here vestigial sideband means not the whole sideband but a fraction of the sideband. So if you take only a fraction of the sideband, so there is a portion of the other sideband. So the correct answer is, it is not a small part of the carrier wave. Neither is it the primary sideband, because the primary sideband is SSB, single sideband, and neither is it noise. So it is a portion of the other sideband. The vestigial means a small portion of something. Next, consider a periodic signal xt of time period t. The signal is passed through an infinite connected ideal unity gain filters with center frequencies 1 by t, 2 by t, 3 by t, and delays t by 4, t by 8, t by 2. Okay, so the signal is passed through an infinite number of parallelly connected ideal filters. So you have filters. Also, and each filter has a cutoff frequency or center frequency rather at 1 by t and delay at t by 4, then 2 by t and delay at t by 8. So basically this is the center frequencies are in AP and the delays are in GP. Also assume that the bandwidth of each of the filters is sufficiently smaller than 1 by t. So 1 by t is much larger. So 1 by t is like the carrier frequency, center frequency, and it is much larger than the bandwidth. Then yt is the sum of all output of the filters. So xt is connected parallelly to infinite number of filters. So here you will see that xt, you have a signal xt, that xt is parallelly connected to filters. So first filter is fc equal to 1 by t in delay tau equal to t by 4. Next it is connected to another filter which is fc equal to 2 by t and tau is equal to t by 8. Next it is connected to fc is equal to 3 by t tau equal to t by 16. Now these all have, this one has, let's say, y1, y2, y3 like that. Now there are infinite such. There are infinite such filters. Now so there are infinite such filters, and all the outputs from all of them are combined to one sum. Okay, so all of the outputs are combined to one sum. Now this sum is yt. We have to find yt. Okay, so this is the problem. Find yt. Yt equal to how much in terms of xt and capital T. And another thing is given. Each of the filters have bandwidth Fn. Bandwidth, say BW, bandwidth of filter, bandwidth of filter is much less than. You can assume it to be, say, B is much less than 1 by t. So it is much less than the center frequencies. So this is the problem. We have to find what is yt, the value of yt. So take 5 minutes and please attempt this question. Once Uh, so, so please solve this. Please solve this, and I will give you 5 minutes. I will give you 5 minutes. After that, if you have any answer, please tell me, and if you don't, then please follow along, and I will discuss the solution. Take 5 minutes, and please attempt the question on your own. Thank you. Now we will discuss the solving of this question. Get the solution of this question. We'll discuss. Let's see. Did anyone get anything? Could anyone get the solution? Hello. Okay. So no solution. Fine. Let's start the solution. So here we have to just find yt, and then we have to identify which modulation pattern is it. So yeah, so yt is now we need to read something called, before we solve this we need to read on something called Hilbert transform. So for your convenience, I'm opening some book or something so that you can follow along. So Hilbert transform is basically like when you take a signal, you break it down into different frequency components, right? Like in Fourier series. But if you break down all the Fourier series components and then phase shift them by -90, so the positive, at least the positive part is shifted by -90 and the negative part is shifted by +90, then you get something called Hilbert shift. So Hilbert transform is basically the Fourier series. You take the Fourier series, you phase shift it by -90 degree. So that is Hilbert transform. Now, other than that, SSB-SC, VSB-SC is what we have discussed previously. So SSB-SC and VSB-SC is now only Hilbert transform we needed, and Hilbert transform is basically take the Fourier series, shift the positive frequencies by -90 degree, and shift the negative frequencies by +90 degree. You will get Hilbert transform. Now, the phase shift. So here we have the center frequencies at 1/2 t, 2/t, 3/t. Okay, so at a particular nth filter block, here you have many filter blocks. So at a particular nth filter block, like this nth filter block, here something is there, fc equal to n/t. So fc will be n/t at the nth filter block. So fc will be n/t. So what will be the phase shift delta phi? The delta phi at n/t will be 2 pi into the n/t into the delay. Now phase shift is basically happening because of the delay. So you have something like omega t minus t naught delay. So that fc is getting multiplied with the t naught. So what is the phase shift? Phase shift is omega t naught. Understood? So this delta phi is nothing but omega t naught. And what is omega? Omega is 2 pi fc, like that. Okay, 2 pi fc t naught. So your fc is n/t. And what is your this pattern? This is sorry, this was not a GP. This was also an AP, t/4, t/8, t/12. I might have mistakenly written it as t/60. So it is not t/60, it's t/12. So 4 1s are 4, 4 2s are 8, 4 3s are 12. So it's just, so it's t/4n. So t/4n. Now the final phase shift will be dt cancel, nn cancel, pi/2. So the phase shift is pi/2. So if you take the phase shift as pi by 2, so omega t minus pi by 2. So what is happening is at every frequency it is omega t minus pi by 2 is happening. So this at every phase frequency, if you are at every frequency, if your phase gets shifted by negative pi by 2 or plus pi by 2 in case of negative frequency, then you have achieved Hilbert transform. So this is basically a schematic to achieve Hilbert transform. Okay, since it is pi by 2, all frequencies shifted by plus minus pi by 2 implies Hilbert transform. So yt Hilbert transform. So yt is the Hilbert of xt. Yt is the Hilbert of xt. Okay. So let's go to the next question. Find the Hilbert transform mht of the signal cos omega 1t cos omega 2t. So what is the steps of calculating Hilbert transform? You decompose into frequency part, you decompose signal into its frequency parts, to its frequency components. This is the first part. Next, second step is shift positive frequencies by minus pi by 2, shift negative frequencies by plus pi by 2. So in that way you have achieved. So you get Hilbert transform. Next, you have mt equal to the product of two cosines. So mt is equal to okay. So you just write it as 2 cos a cos b. And you simplify it as cos omega 1 plus omega 2t, omega 1 minus omega 2t. Now these are the fundamental frequency components: half cos omega 1 plus omega 2t, half cos omega 1 minus omega 2t. Now if you want to do Hilbert transform, you just phase shift. You assume omega 1 is greater than omega 2, so both of them are positive. Okay, omega, and here also it is written assume omega 1 is greater than omega 2. So you just take that, so both of the frequencies are positive, so you will phase shift both of them by negative pi by 2. So both of them are phase shifted by negative pi by 2. Now this is equivalent to, since cos is an even function, cos a minus pi by 2 can be written as cos pi by 2 minus a. Now what is cos pi by 2 minus a? Sine. So it is half sine omega 1 plus omega 2t plus half sine omega 1 minus omega 2t. Now you can sine a plus b, sine a plus sine b. So this is half into 2 sine a cos b. So 2 sine sine a plus b plus sine a minus b is 2 sine a cos b. So it is sine omega 1t cos omega 2t. This is your answer. Sine omega 1t cos omega 2t. Correct answer is answer C, option C. Next, a single sideband signal is generated by modulating signal of 900 kHz carrier by the signal mt equal to the single sideband signal is generated by modulating signal of 900 kHz and carrier by the signal mt equal to this cos 2000 pi t plus sine 2 into sine 2000 pi t. The amplitude of the carrier is 100. So the message signal is given as a sum of a cos and a sine, and the amplitude of the carrier is 100. So find the lower sideband of the SSB-SC. So a single sideband signal is generated by, so you have FM, modulating signal FM. You have FC, modulating signal FC carrier, a 900 kHz carrier, and this is your message, and this is AC. So AC carrier frequency wait oh, this is not FC, sorry, this is not FC. So modulating signal, this is the modulating signal concept, and the message signal is given and the carrier amplitude is given. Now try this. You have to, so to try this you have to know just one formula, that is the, for single sideband you have A, the LSB is the AC into, what we have is usually mt cos 2 pi fct, right, plus you will have MHT, that is MHT is the Hilbert transform of mt, MHT sin 2 pi fct. So this is the formula. Okay, I'm giving you the formula also for the LSB, your sideband. Now please put the value of mt, calculate the value of MHT, and put all of them together and get an answer. Okay, so please try this. Please try this for 3-4 minutes, then we will try to go to the solution. If you have the solution, please open your mic and tell the answer. And you have to justify why. The answer is actually visible in the screen. You have to justify why that is the answer. Okay, so let's go to the solution. The mt is given to be cos 2000 pi t. mt is given to be cos 2000 pi t. cos 2000 pi t plus 2 sin 2000 pi t. 2 sin 2000 pi t. Now, writing 1000 pi t every time 1000 pi is pretty so pretty irritating. So what we will do is we will put fm equal to 1000. So omega m is equal to 2 pi into 1000, so 2000. So it's just cos omega mt plus 2 sin omega mt. Now what we have to do is we will substitute this at the last stage of the problem. Now we have to find the lower side bit, so we need to find the Hilbert transform. So the Hilbert transform will simply be, since these are isolated frequency terms, so you can just subtract pi by 2 to get the Hilbert transform. Okay. So this will be sine omega mt and this will be minus 2 cos omega mt. So this is the Hilbert transform. Now the LSB, what will be the LSB? The LSB will be AC common mt cos 2 pi fct, that is omega ct, plus mht sine omega mt. Sorry, omega ct. Wait, let me adjust this. Okay, it's done. Now, sorry, so this is done. Now we will just expand this. So XLSBT is AC. So you have cos omega ct and this one is cos omega plus 2 sin omega. So one term will be cos omega mt cos omega ct. Cos omega mt cos omega ct. Another is 2 sin omega mt cos omega ct. And another is the Hilbert transform is sin omega mt minus 2 cos omega mt. So sin omega mt sin omega ct. So it will have sin omega mt sin omega ct. And finally minus 2 cos omega mt sin omega ct. Now let's group this and this two. So you have AC cos omega mt cos omega ct. These two and these two will be another group. These two will be one group. Okay. So cos omega mt cos omega ct plus sin omega mt sin omega ct. So this will be cos omega m minus omega c. And another is 2 sin omega mt cos omega ct minus cos omega mt sin omega ct. So this is sin 2 sin omega m minus omega c. Or you can just write in a different way. minus omega c minus omega m, since m is an odd function. Omega c should be, and this one will be omega c minus omega m. Now this will be cos 2, this will be 2 pi fc and this will be 2 pi 1000. So let's do 2 pi common, fc minus 1000 t minus 2 sine 2 pi fc minus 1000 t. This is the final expression. Now let's compare. So AC is 100 cos 2 pi fc minus 1000 2 pi fc minus 1000 t minus 200 minus 2 sine 2 pi fc minus 1000 t. So the correct answer is option C. Option C is your correct answer. Okay. Next, consider the following baseband signal with minimum and maximum frequencies 0.3 and 0.4. This signal is modulated with center frequency 2.3 kilohertz. So this signal is modulated with a carrier frequency of 2.3 kilohertz. Find the minimum and maximum bandwidths of the filter that can be used to perfectly construct the lower sideband SSB modulated signal. So you will take an SSB modulated signal and you will take only the lower sideband of that, and you will need a filter. So which filter can be used to perfectly construct a lower sideband? Okay. So let's do that. Here the modulated, the center frequency is 2.3 kilohertz. Okay, so when we do a normal amplitude modulation, what will we have? We have one at 2.3 kilohertz. Right. This is at 2.3 kilohertz. Now you need two sidebands. The sideband center frequency will be the center frequency of this thing. So it will be 0.35. So 2.3 plus 35 is 2.65. So the center frequency will be 2.65. And it will go from 2.6 and end at 2.7. So 2.6, 2.7. Now 2.3, 2.6, 2.7, 2.65. This is the sideband. So to construct a filter, we can either use a band pass filter. If we use a band pass filter like this, then the bandwidth needed is 0.1 kilohertz. Okay. And if we use a low pass filter, we have to go till here. And okay, and now we have to, this is the upper sideband, sorry. Let's construct the lower sideband. For the lower sideband, we will have 2.3 minus 0.35. So it will be 1.95 will be the center frequency, because this center frequency is 0.35. So 1.95, and it will start at 1.9, end at 2.0. Now the minimum frequency is that of a band pass filter, which will exactly cut through, and the maximum frequency is that of a low pass filter. Now since we are taking SSB-SC, we will take low pass filter up to see, since we are taking SSB-SC, we will take the low pass filter. We will only take the lower sideband. So if we take the lower sideband, we have to cut off at here. So, or low pass filter, if we only want to take LPS, so if LPF, then we have to cut off at here. So your bandwidth is 2.0. Now can we go higher? This is bandwidth 2.0, 0.9, 2.0. Now if we design a high pass filter that allows all frequencies above 2.6, then also we will get our sideband. This is a band pass filter which requires the minimum frequency bandwidth. And then you have low pass filter. But if we use a high pass filter, we can go even higher. The bandwidth will be even more. So it will be 2.6, because anything below this will be rejected. Okay. So the maximum bandwidth is 2.6. So maximum is 2.6, minimum is 0.1. So correct answer is option A. You see the maximum, this is the minimum. Minimum is just a band pass. And the maximum is a high pass. Okay. Next. Let 10 signals, each band limited to 6 kHz, are to be transmitted over a single channel with frequency division multiplexing. So 10 signals, each of them are band limited to 6 kHz. Each of them band limited to 6 kHz are to be transmitted over a single channel by FDM. So each of the 6 kHz is transmitted over FDM. So we will divide the available bandwidth slots into 6 kHz slots. Divided bandwidth into 6 kHz slots and transmit these signals. Now SSB-SC modulation is used. So SSB-SC modulation is used and a guard band of 2 kHz is used. So what is the bandwidth of the multiplex signal? So we will have to find the bandwidth of the SSB-SC signal. Then we have to add 10 SSB-SC signal bandwidths and 9 guard bands. Because if there are 10 SSB single sidebands, if there are 10 single sidebands, like if you have 3 single sidebands, there are 2 guard bands. Okay, here and here, here and here. So 10 SSB-SC bandwidth plus 9 guard band bandwidth. That is the 9 guard bandwidth. That is the bandwidth of the total signal. Now each of them are band limited to 6 kHz. So 10 of them will be 10 into 6, 60. And 9 of the guard bands each are having a bandwidth 2 kHz. So 60 plus 18. So it is, the answer is correct. Correct answer is 78. So correct answer is 78. Since there are 10 SSB-SC signals, each band limited to 6 kHz, and you have 2 kHz of guard band in between. So 10 into 6 plus 9 into 2. 78. Now consider the comm signal mt is equal to m1t cos omega t plus m2t sin omega t, where with the carrier frequency omega being much higher than the bandwidths of omega 1 and m1 and m2. So you have a comm signal where m1 and m2 are two small message signals, and they are modulated by carrier with frequency omega, with omega being much higher than the bandwidth of m1 and m2. Now the in phase part, that is m1, is recovered by multiplying the signal mt with the frequency imperfect carrier ct equal to cos omega plus delta omega t. Now how do we get a frequency imperfect carrier? Because at the receiver end we try to estimate or guess or predict what the carrier frequency of the incoming signal is. and based on that we generate carrier frequency in a local oscillator. Now the local oscillator is not a 100% accurate, so you will have some inaccuracies in reproduction of the local frequency. So this is the inaccuracy of reproduction of carrier frequency. Carrier frequency by local oscillator that causes this delta omega. Now you have imperfect carrier cos omega plus delta omega and it is passing through a low pass filter. Find the recovered signal. So you have MT, you multiply it with CT, so you have MT, you are multiplying that with CT and you are getting some signal, say YT. That YT is getting demodulated by an LBF, rather filtered by an LBF, and you get some, let's say this is HT, the intermediate is HT and the output is YT. So after filtering HT you have YT. So it is saying that this YT is the recovered signal, so find YT. Okay, so first we will get HT. HT is the product of MT and CT. So we will first get HT. HT HT is the product of MT and CT. So MT into CT, let's calculate that. So here we have MT is some in-phase and quadrature signal, IQ signal. So MT cos omega t plus M1t cos omega t plus M2t cos omega t, sin omega t. So this is some in-phase and quadrature components, and you are multiplying that with cos omega plus delta omega t. Now HT is M1 t cos omega t cos omega plus delta omega t plus M2t sin omega t cos omega plus delta omega t. Now we will use trigonometric identities. So this will be M1t by 2. So this is 2 cos A cos B. So 2 cos A cos B is what? Cos A plus B plus cos A minus B. So it is cos A plus B, that is 2 omega plus delta omega t plus cos A minus cos B, so cos delta omega t. Similarly, this one is 2 cos A sin B. So this is 2 sin A cos B. So this is sin A plus B plus sin A minus B. So this is sin A plus B omega cos A sin A cos B is 2 sin A plus B. So 2 omega plus delta omega plus sine A minus B. So that is sine minus delta omega t. So you have m1t cos delta omega t. This is there. Now when the filtering will be done, this will be present. Along with it will be present m2t, rather minus m2t sine delta omega t. This one again is not of the order of the carrier frequency, so it will pertain because the lower LPF will have a cutoff. LPF cutoff is given as LPF cutoff is nothing is given, so you can assume that LPF cutoff is omega. So you have m2t m2t by 2 sine 2 omega plus delta omega t plus m2t m1t by 2 cos 2 omega plus delta omega. Now here you see these two, when you do a filtering, these two will get cut off after filtering. After filtering, you have these two will get cut off to 0, 0 and 0. So you have final signal after filtering is yt is equal to m1t cos delta omega t minus m2t sin delta omega t. So again you have the same in-phase quadrature that you had, but instead of omega you have the in-phase quadrature components in terms of delta omega. That is the only difference. But it is still m1t cos delta omega t minus m2t sin omega delta omega t. Now here m2 cos of delta omega but m1 sin delta omega. That is not correct. And these two have both plus, so these two are also not correct. So the correct answer is none. The correct answer is none. So here the correct answer I will write half m1t cos delta omega t minus half m2t sin delta omega t. Okay, so that is your correct answer. So that concludes our problem solving session for this class. But since there is some time remaining, then I think we will tackle some additional problems since there is some time remaining. So we will take some problems of Hilbert. Rather, okay. So here we will solve some multiple choice question. uh, a Hilbert transform is a dash system. So a Hilbert transformer is a dash system: A non-causal, B time varying, C low pass, and D non-linear. So what is a Hilbert transform? Is it A non-causal, B time varying, C low pass, and D non-linear? Now for that we need to first tackle what is a Hilbert transform. Now we have defined it in terms of phase shift by 90 degree. But another way to define Hilbert transform is MHT is equal to mg convolution 1 by pi t. So when you convolve with the signal 1 by pi t, what you get is Hilbert transform. So that is another way of writing Hilbert transform. This is the first principle definition that can be for sinusoids, that can be simplified to addition or subtraction of phase shift. So if you put mt equal to a sinusoid, you will get this to be addition or subtraction of phase 90 degree. So that is a special case. The phase shift by 90 degree is a special case for sinusoids. The generalized Hilbert transform is defined as mt convolution 1 by pi t. Now, is it time varying? Is the first question. So, is it time varying or is it time invariant? See, here you see that the function mt is getting convolved with is explicitly a function of time. So for time invariant signal, there should not be a time expression outside the message signal. The message signal should be not operated upon some time varying function. So here we see that it is a time varying function that is being operated on the message signal. So we can say that the system is time varying. So the system is time varying. Now, for message signal mt is equal to cos 2 pi fmt and carrier frequency fc, which one of the following represents a SSB signal? So, okay. Now, the general. So the second question is for message signal mt equal to cos 2 pi fmt and carrier frequency fc, which one of the following represents SSB signal? So here you have the message signal and you have a carrier frequency. So what is the SSB signal? Let's derive that. So mt is given to be cos 2 pi fmt or omega mt. You can write cos omega mt. Now, NHT, since this is a single frequency component, we can just phase shift it by negative pi by 2 to get the Hilbert transform. So this is just sine omega mt. So the Hilbert transform of cos theta is sin theta. That much is understood. Now, SSB-SC. Now they have asked for SSB-SC. So SSB-SC will be MT will be the in-phase component, MT cos 2 pi fct or omega ct, and MHT will be the quadrature component. So this is done. Now let's put the values. MT is cos omega MT, cos omega ct, and MHT is sin omega MT, sin omega ct. So it just becomes cos A cos B plus sin A sin B. So this is cos A minus B. So it is just cos omega C T. Okay, so it is cos omega C minus omega T. Now cos omega C minus omega M is if you take lower sideband. If you take upper sideband, that's the fun. If you take upper sideband, it will be this plus or minus. This plus stands for lower sideband, and this minus stands for upper sideband. Okay, so if you take plus minus, you will have minus plus. So cos omega C minus omega mt and cos omega C plus omega mt, both are valid SSB. One is upper sideband and one is lower sideband. So that gives us the answer cos 2 pi fc plus fmt. So it is option 3. Okay, so this is option 3. Now SSB will have carrier LSB and USB, LSB and USB, LSB or USB, or none of them. So single sideband, since it is single sideband not option, so it has only one sideband, so it will either be USB or USB. So correct answer is option 3. So correct answer is option 3. Okay, only one single sideband will be there. Next, a single sideband AF signal is given by 1000 sin 1000 pi t cos 11,000 pi t. So yeah, okay, this question is, I think, there is a typo. I don't think this is the way. The impulse response of a Hilbert transform is given as this thing. Okay, so this one I think has a typo. We will not go there. Achha. So here you see that another way of writing Hilbert transform. So this 1 by pi t, when you take the Fourier transform, the Fourier transform of 1 by pi t is minus j signum omega. So here signum omega means you take the sine of omega. If omega is negative, it is minus 1. If it is positive, it is plus 1. So it is just basically plus minus j. So the Fourier transform of 1 by pi t is plus minus j. So if you have a signal in real domain, basically when you are if you have a signal in real domain and your say your signal is real, or even if your signal is complex, so complex signal, now the Hilbert transformer is MHT is equal to MT convolution 1 by pi t. So if we take a Fourier transform and convert it to the frequency domain, we will observe that MHF is equal to MT into the Fourier transform of this thing, Fourier transform of 1 by pi t. Okay, so it is the Fourier transform of 1 by pi t. Now, what is the Fourier transform of 1 by pi t? It is j signum omega. Okay, so it is j signum omega minus j signum omega. So, or 2 pi f minus j signum 2 pi f. So here this signum 2 pi f is basically plus 1 or minus 1. So what happens is you are essentially like minus plus, essentially you have minus plus jmf. So you are just multiplying with a j. Ultimately, if you disregard the sign, all Hilbert transform does is multiply your Fourier transform by a j. That's why when you take the decompose it into Fourier series, you can see that you can get the Hilbert transform by phase shifting by negative pi by 2. So that is the essence of Hilbert transform. But this Hilbert transform, this means the expression states. So here for omega less than 0, okay, there's manner with the expression member who's transformed this device. Also the magnitude such an ideal device is, so you have to make a Hilbert transform, you have to make a device which produces a phase shift of minus 90 or positive 90 depending on the sign of the frequency, and it will have no magnitude loss, so the magnitude will be same. Such an ideal device is known as the Hilbert transform. The Hilbert transformer may be viewed as an ideal all-pass 90-degree phase shifter. So it phase shifts by 90 degree and it passes all the magnitudes. So the Hilbert transform is not causal, but the Hilbert transform is not causal. That is, it is not physically realizable. Why is it not physically realizable? Because it depends on the future value. So if you convolve with 1 by t, you will see that it extends both to, even for a causal signal, it extends both to minus infinity, t equal to minus infinity, and t equal to plus infinity. So it extends throughout the time. So the existence of negative time at the signal denotes that it is not a causal signal. So we will not get any answer. We will not get any physical realization. I'm sorry. We will not get any physical realization. So such an ideal device is known as Hilbert transformer. So the Hilbert transform is mainly used in the field of signal processing, analysis and synthesis of signals, design of filters. Some chief signal applications of the Hilbert transform are: Hilbert transform is used to represent bandpass signals. Hilbert transform is used to represent bandpass signals. Why? Because you have an in-phase component and a quadrature component. So you are basically creating sidebands. So you have an in-phase component and you have a quadrature component, and you are creating that bandpass response. So it is used to represent bandpass signals. Hilbert transform is used to realize the phase selectivity. So here Hilbert transform biggest application is it is used to make single sideband modulation. SSB modulation is realized using Hilbert transform. So the Hilbert transform is also used to relate the gain and phase characteristics of communication channel. Okay, so that is I think beyond the scope. And so here you see the Hilbert transform of sine omega t is minus cos omega t, and for the Hilbert transform of cos omega t is minus sine omega t. So it does not affect the frequency of the signal. That will be all for Hilbert transform. So yeah, that will be all from my side for today's class. And with that I will be ending the class. If you have any doubts, you can raise in the discussion forum of nptel. I will be there to answer. Thank you.